Thanks for having me today here. It's great to get back to many friends and colleagues and give the opportunity to give a talk. Well, as probably most of you know, now I'm director of Telefonica Research, and I'll give a brief introduction about what our team is doing here in Spain. And again, so that maybe it would be great if you could create some collaboration around some of those topics, especially maybe in the context of the upcoming European projects that are starting now again in October. And then after that, I'll get into more a little bit technical details, talking about machine learning, deep learning applied to networks. Let's say in in a broad sense of what network is. So as I said, I'll give a little bit of self-advertisement so that you get to know a little bit our team here. And again, I hope we can get some more collaboration and get into some example of the work we have been doing in the context of machine learning, deep learning applied to, yes, telco networks. Again, we'll see that it's in a large context. And then give some example. And after that, I'll leave some surprise at the end or towards the mid of the talk. I mean, feel free to interrupt me if you have any question on the way, or if you prefer to do that at the end. It's all the same for me. Okay, yeah. So what do we do? Well, in Telefonica Research, we're a group of 15 people plus students, and we do two main things. When on the one hand we do research in the more classical sense of the term, we do publication with more state of the art. We create APR, and we are very active in the scientific community. And also we do a lot of collaboration again with academic and private institutions in different contexts. So it would be great if you can leverage this opportunity to collaborate more. And so that's one of the two main goals of the team. And the second goal of the team is actually to leverage the knowledge that we create and the science that we create to impact Telefonica. And we do that in different form. Very often we do consulting. Often we transfer algorithms. We develop some solution for our business unit. So this is the main goal of the team. We are divided into two main sites. So one is here in Barcelona, and the other one in Madrid. I'll let you pick the one you like the most to come and visit us. I'm the one in Barcelona, but the team is spread across the two regions. And here is just a quick overview of the team members. I'm just listing here the permanent members, not the students and postdocs that we regularly have. As you can see here, we cover 4 main areas, many of which I think are of interest to the links, which are, well, network systems, security, privacy, machine learning, deep learning, and human-computer interaction. And I'm going to give you now some example of project that we run in these areas. Most of those you will see are actually at an intersection of this area, because we have very flat structure, and we collaborate freely among us, and again together with other institutions. So here are some example of the project we do, and again open for collaboration. And there are networking system. We do a lot of machine learning, deep learning applied to networks, and I'm gonna talk quite a bit during this talk about it. Working for telco, we do a lot of measurements and design of mobile and fixed network, as you can guess. We are focusing a lot about beyond 5G, 6G networks and IoT in a broad sense, and working quite a lot on SDN, AV, and edge computing, which are a key enabler of technology for future network and systems. In the area of security and privacy, again, we have a strong focus on privacy preserving machine learning, deep learning, and anonymity. We do, in general, also work in the security and privacy of the web, quite a bit on data marketplace and data exchange and management, which are, again, very important in these days. And again, related to the networking system topic, we'll do a lot of SDN and AV work on security and privacy. Machine learning, deep learning. So we have a core team which does more, I would say, fundamental research in machine learning, deep learning, and those are typically focusing on area of audio, speech, and video, or natural language processing. And then there's some more work in, which is an intersection of the other areas, which is, for instance, federated learning, or again, AI applied to networks. I'm going to talk a little bit at the end of the talk about the work we do in the federated learning space for the privacy preserving. So you'll see a view of what we do at high level on those topics. And then the human-computer interaction, as we see, is not completely unrelated to the other. We do quality of experience, especially related to fixed and mobile networks, and social computing or mobility analysis of customers or social computing in general for the web. I mean, these are a very brief overview of the main activities of the team. And again, we do two things on this. We advance state of the art, and then we do impact in Telefonica. And we're really open to collaboration again in any of these topics. Well, again, just some scientific input. Okay, we publish in the major conference worldwide. I think, well, you know most of those, and we organize conferences. So we do a collaborative project, but also I'm putting here many of the business units we work with when working within Telefonica, where we actually impact those teams out of our research. For instance, working with the AI group of Telefonica, working with the home environment for machine and deep learning, working in traffic data analysis with different of our operators, working in remote area communities with internet operators. I mean, this is just an example of the different business unit that our research work has been impacted, working from those areas. Okay, now after this not so short introduction, I hope that you find some of those areas interesting, and we can talk later on how we could contribute on that. I'm gonna go into a little bit more on the technical side of the talk and talking about machine learning and deep learning for networks and what we've been doing in this area, starting from a high-level view of the overall concept that we had, and then going to a couple of use cases we have been working on. I want to mention that this one was, again, it's a research project, but then we had a lot of work with our business unit creating impact on that. And also we have collaborative project with external partners on this. Now, I always like to start with these slides when talking about networks and the complexity of networks, because very often, at least when I ended my master students, people were telling me, okay, the network is a graph, you have edges and vertex, and you have a magic algorithms that is going to interconnect and solve the problem. Or you have a protocol which is perfectly standardized, it's going to work this way, you're going to follow you for understand the problem. But then as soon as you start, digging into it, or working for a telco or for a vendor, you actually realize that the things are way more complex. And even if you take it from high level perspective, if you think from a let's say telco perspective, you start from your home devices and IoT devices. Some of those sits in your home, the gateway, the smart speaker, and all of these IoT devices. Some of those are actually outside the house, some are the mobile phone. You see here, there are already a lot of algorithms, a lot of protocols involved. It's a war per se. And there are many actors, they are different vendors, you have different providers that sits there. And then, many of those devices actually need connectivity. And the first thing they do is you go through the access network. And the access network, again, can be radio, can be cellular, can be wireless, can be fixed, can be very different. Again, many algorithms, protocols, different actors again. But then you didn't even reach the core of the ISP, when you have multiple ISP and even with multiple mobile network operator. Again, protocol algorithms are different there. And then, the core network, you might have platform on the top. I mean, I don't want to go into detail of this, but I hope I can convince you that it's a very complex ecosystem. There are so many protocols, algorithms going on this, many actors, many companies involved, the users involved, and even within the same company, very often for a single product, there are multiple teams, and it's very complex to manage all of this. Now, how can we do that? Well, there are the traditional operational approach that have been working for years. This is great. But we believe that machine learning and deep learning is actually something that could help and give some more insights to the operation, help the operation to improve the management of their system. I'm not saying to replace, but it's actually to help them to do their daily job, but also to provide better quality to the customer in the end. And across the work we have been doing, we've been working across the full spectrum, because Telefonica, we have different of this business unit working in the different part of this network. And you can develop a lot of use cases or places in each of these segments where machine learning and deep learning can actually be beneficial. But apart from that, many of the benefits comes when you start putting together feeds of data and knowledge coming from different pieces of it, because very often for a single product, you traverse all of these steps, and it's very important to put together information from the different part of those. And then that's where you can actually improve significantly the operation, the management of those networks. But even in the single case use cases, it's already somehow beneficial. Now, high-level view of some of the traditional use cases that we have been working on. So we worked a lot with the IoT platforms, which is basically a platform which provides global SIMs to IoT providers, which provides a management dashboard and suggestion and the way to predict and to manage all the SIMs. And here, what they were interested in and we've been working on is basically, again, prediction and anomaly detection. And we have been using traditional machine learning, time series technique, clustering, and a little bit of deep learning, but mostly were more, say, simple techniques. We have been working quite a lot with core networks. There, the people are most interested in detecting anomalies like denial of service attack, hijacks, And depending on the data feeds that are available, we've been using traditional machine learning or a bit of deep learning, but mostly machine learning again here to detect anomalies in the traffic pattern of the core networks. And there is an important trend of work that we've been doing in characterizing the quality of experience of the users. But very often as a telco, you don't have access to the data on the phone of the user. So you try to do that from the network states. So the network, sorry, not network information, network level information. So what we're trying to do is to understand the quality of the user from network level data. And, you know, we tested all of a battery of machine learning model. So I want just to show you some example at high level of use case that we've been working on. I'm going to go later on into two of them a bit more into details. And again, the approach we use, we started from simple traditional techniques, and we reached in some cases deep learning. And in some cases, you know, we're falling back on a heuristic of something that we learned on the way. And in some cases, we were able to, you know, use some simple machine learning tricks in case we had to go to deep learning. I mean, these are just three examples of what we've been doing in this area. And now I would like to focus on one specific use cases, which is a very peculiar network environment, which is complex per se, but also I think it's an environment where we're not really, you know, typically not very familiar with. So we have a project in Latin America. It's called Internet para Todos, which, as the name say, is try to bring some mobile broadband connectivity to unconnected remote areas. And the project basically builds an infrastructure which can be shared across multiple operators. And it uses open access technology and a sort of a revenue share model with mobile operator that use the infrastructure. Now, what are the characteristic of this network is that it connects thousands of small communities, which are equipped mostly with 2 and 3G, and in some cases 4G connectivity. What's very interesting in these communities, they're in really remote areas. Some of them are even in the rainforest. And also what is very interesting is that most of them don't have access to a main road. So you have the small cell well, the cell, actually not small cell, the cell sites in, you know, 5-10 kilometers away on average from the main road, but in some cases you reach it even the 70 or 80 kilometers away from the main road. So you can understand that management of those areas can be very problematic, especially in cases of failures. They have different power supplies. In some cases, they have solar panels. In some cases, they are connected to power grid. In some cases, they have battery or a combination of those. They use all sort of third-party backhaul network from satellite, radio links, and in some cases, there is also fiber. So what I was saying, management of those networks is pretty complex because of that very far away remote areas, not well connected with main roads. And so what the operation tried to do is to do any, you know, intervention in case of problem from a centralized location, and only when there is no further resources, try to schedule an intervention and do some intervention in batches. But as you can imagine, their cost is something which is important there, because where the revenues are somehow limited, but also the cost is very high. So you try to, you know, make the best out of it from the data you have it to optimize the operation in the most possible efficient way using a data-driven approach. And so for this, the project has developed a sort of collector, centralized collector from the different vendors in these different sites. And they are collected in a centralized location where, you know, all the alarms are cleared and, you know, prepared for staying there. And basically, what's interesting is that you have the alarms in 2 states, either active or solved. And some of those alarms, I'm going to show you later, are actually failure, meaning the cell site doesn't work. Now, on the top of this amount of data, what I was saying earlier is that the project uses a very important data-driven approach where build on the data, you try to enhance operation. And there are different ways that the project enhances operation. Well, you have the traditional management dashboard, which are, you know, fairly traditional approaches. They develop also a rural bot where the intervention team can, you know, go on his phone and check what the bot suggests them to do, where to go next to fix an intervention. And interestingly, there's this possibility to have what's called decision engine. So basically doing some analytics or machine learning on the top of the data, which recommends solution to the operation teams or gives suggestion to the operation teams. Now, based on this, we worked on developing some analytics tools for them and for this specific specific area. And so we looked at 5-month data coming from this large infrastructure network. And in this 5-month data, there were 3 main failures. One of them was pretty generic, the cell doesn't work. The other one was more related to the power failure, and this can be a very different kind of problem. It can be just the battery that's not, it needs to be replaced. It can be that there is no sun for a while. It's been raining for 2 days, and there is no more power. It can be there was a power outage in the grid. It can be very different. And another one, the failure one, is that basically it's a protection for the antenna, that whenever there is too much power, it turns down to avoid damages. Basically, so this failure represents roughly 4 to 5% of all the alarms, which are millions of alarms over this month. And the dominant one is the generic one due to the cellular out of service. Now, what the operation team have to do? In principle, whenever there is a failure, they should schedule an intervention and go and fix the problem. However, looking at this failure, I don't want to go too much into the details of those graphs, but what's important to mention is that the failures are very, very short. Actually, 90% of them last less than 1 hour. And only 1% of them actually last more than 24 hours. And also these failures are very intermittent. It goes down very fast. And the reason is that most of those are due to backup saturation or temporary battery outage of lack of power, or again, heavy rain, which creates a problem. Now, the problem here for the operation is that these sites are very remote, as I was telling earlier, so they cannot schedule an intervention as soon as there is a failure. They need a way to get to know if this failure is going to be permanent or not, and if it's worth sending a team to that intervention or not. Would just be a waste of time, because the time the team starts going there, the failure gets solved by itself, because it's something that's just them. So it's critical. So what we wanted to develop there is a mechanism which helps the operation to understand if a failure is permanent or not, and inform the operation team whether to intervene or not. And also, another important problem is to understand the nature of the failure, because you cannot carry, for all these kilometers, all sorts of material to solve all sorts of problems. You really need to understand what kind of failure you're dealing with. Okay, well, here's just an analysis over time of the failure, which is mostly during the day. So we tested different techniques, including deep learning. And in the end, the ones that we found are working better is XGBoost, which I think most of you are familiar with, which is a more traditional machine learning approach. Deep learning wasn't really getting any benefits here. And the goal here was to detect, it was a typical binary classification problem. The luxury here is that we had ground truth, because we had the past, while very often when you work with network-related problem with the machine learning deep learning, you don't have ground truths, which is usually a huge pain. But here we had this luckiness for that. And we developed a solution which is based on the alarms and additional information from the cell site. What's interesting there is that there was a lot of importance also from features like the weather, the time of the day, the distance from the road. So some sort of characteristic of the cell sites, which was impacting actually the technical failure is important or not. And here basically, what the metric that we used to evaluate whether this was a useful solution or not was basically, we have evaluated using traditional precision and recall, but for the operation of a typical precision recall doesn't really matter much. What matters then is the cost. So is this solution providing them benefits in terms of cost or not? And there are two main forces here driving the benefits. On the one hand, there is the cost of sending somebody to fix the problem, and the other cost is actually the time the site will stay down. You might lose customer because of churn. You might lose revenue because people are not using the lines. And depending on this trade-off, you can get more or less benefits. And of course, we cannot reveal what are the benefits of our network. But depending on this trade-off, you have more or less benefits. But what's interesting to observe that even for a small ratio, you start getting and having some benefits. And of course, then when the revenue loss gets significantly more higher than intervention cost, then you gain a lot. But in general, for two reference scenario, what's important to say is that you have between 5 and 20% of benefits in using this approach with respect to just waiting 24 hours before to send someone, which used to be the traditional approach of the operation team. This is one key message here that I wanted to share. And the second is that, okay, we derived after the analysis a set of heuristics, which actually turned out to be better than the solution the operation team had in place, which was to wait for a given amount of hour, and that was also one of the sites. So basically, what's important here, the key message here that I want to share is that machine learning deep learning can actually, most machine learning in this case, and then it can actually help in this important scenario. And you can have benefits which ranges in the few percentage, like 5 to 20%. What is also important here, I wanted to stress, is that during this process, we also learn several heuristics that could help the operation team to improve the way they do the operation daily without necessarily using the model. And yes, this was one important use case, which I think it's complex in a specific way, and that where we see this kind of techniques applied in real world scenarios can be beneficial. Now, I'm happy to talk more about this. You can find more information about in our Mobicon paper we had last year. Well, you can find it online or contact me. Yeah, happy to talk more about it. Now, I wanted to talk a little bit about another very interesting environment, which is the IoT environment. I don't know how much you're familiar with this, but the IoT ecosystem is very complex. And there are many IoT providers, which are, IoT platform provider, which provides a SIM that can be installed in IoT devices, and then this can be used anywhere in the world and seamlessly. And that's so it's very useful for the IoT provider because they don't have to really bother to do any agreement in every place they want to deploy their devices, but they just buy this from the global platform. And they are called global SIM. And actually, it's interesting because all of these global SIM, whenever they are deployed in a different country, they are roaming. So very often people say, but IoT devices don't roam. I mean, yes, actually they roam, even if they don't move, because the SIM that have been provided to them, it comes from a different country. And this put an important stress of the network, because I'll show you later in the next slide, the ecosystem for these devices is very, very complex. Actually, we have in the papers that you can find there at IMC and then the CCR, actually we have an upcoming SICOM paper on this. We showed and we analyzed a bit this IPX in this roaming ecosystem and the impact of IoT devices and how many of these IoT devices are on this ecosystem. So please refer to this paper and the upcoming SICOM. Here is, to show you the complexity of the ecosystem. So this platform gives you a SIM, you install, the IoT providers install it in its devices, which are on the left-hand side of this graph. And then, if they are connected in a different country, they are in a visited network, which then has to establish a relation to the home network. And to do that, they have to go through what's called IPX provider, which is a way to enable roaming globally and more. But okay, the main use of this IPX provider is providing roaming worldwide, and which is a network per se. So you see there are different entities, at least 3, if not more, different IoT verticals. And also, it's important to say that most of those devices are 2G, 3G enabled, not 4G. So now we are talking about 6G, and you will see that most of the devices are still in 2G, 3G. So the complexity of managing multiple different technologies is there and makes things even more complex. And I hope I convinced you this ecosystem is pretty complex. So what we were working on is to devise an anomaly detection for these IoT devices. And it's very interesting because depending on which part of this chain you are with, you have a very limited visibility. I mean, not very limited. I would not say very limited, but you have a partial view of the whole ecosystem. And what's main challenge there is actually with the data you have, how can you do anomaly detection on that? It's actually mostly related to CNN traffic, for instance. Also, what's very interesting is that whenever the SIM are shipped to customers, so very often you don't know what the customer is, because you don't have access to the final customer, being in the middle of the chain. But even if you have access to the final customer, you don't really know how the SIMs are used. You might guess that. And so even within, you have to do per customer solution. But at the same time, within a customer, a single solution might not work. So you need clustering and unsupervised approaches. Here, actually, we use a combination of clustering and autoencoders and then post-processing for explainability. Which actually brings me to the next important element, which is the usability and explainability, because I think most people that work with these technologies is that very often you work in use case driven, and whenever you talk to network engineers or people running this kind of network, they don't necessarily have the right background to deal with data science. They are amazing in the knowledge they have about the protocols on the network, but of course they don't have the data science background. So you need to give them tools that are useful to them and that are explainable and usable. And also you have to understand what they give you. So this interaction, it's very interesting, and we need some explainability to the solution that we added to add to make this very useful for them. Another problem in this kind of solution, differently from the lucky we had in the previous use case that was mentioned, is that there is some ground truth information, but there are not ground truth for all the anomalies and so all the issues that you will see on this. And so how do you validate and how do you build it? solution for that. That's story of our life whenever we work about AI and networks, and this is what typical. And then of course you have the operational requirement, whenever where you want to develop those. So even for this solution, we use a combination of I don't have time now to go into all the details of the solution, but we use a combination of clustering and autoencoders and some explainability after. Flying about that. AI is amazing. Let's say, or deep learning, machine learning. I'm able to use AI because I'm on slides, but in the practice is machine learning, deep learning. It actually, it can help separation in networks across multiple scenarios. But there are two main problems. Okay, I'm mentioning here only one, the vulnerability one, but there is another one which is important, which is that I want to mention first, is the robustness. These are all sort of all of these solutions give you some statistical properties. You can have very high precision accuracy. Still, you will have few percentages which are missed, and you need to retrain the model continuously. So this, to me, the solution is at the moment is that you couple that with whatever you had up, and it's not something that alone solves the problem. It's something that building on the top of what operation already have can help, and I think that's very important. And the second problem is that machine learning are vulnerable. Actually, there is a new attack surface that you didn't have before, which is the model attacks, and there have been quite some work and also attacks up, and that can allow people to detect if if an element was present in a model, which is the known as membership inference attack, data reconstruction, being able to reconstruct the original data, get some property out of the model. So you're adding an element which can be potentially malicious, which can potentially lead to malicious attacks. And also, whenever you deal with this problem, you have sometimes the users involved, or maybe some private data in your network, and you don't want this information to be leaked. Okay, so I give you an optimistic view first. Hey, hi, it's great, can help operation. Now, oh wow, it can be vulnerable. It's not robust. Okay, right. I mean, for the robustness, I already mentioned what the solution is, and things are keep improving. And for the vulnerability, there are solutions, and there is an important thread of work around these areas. And a few of the areas that we are working on, and I'm going to give you the example in the next minutes of the talk, is the use of federated learning or trusted execution environments or differential privacies as mean to limit, let's say, the vulnerability and the privacy leakages that these techniques can give. And okay, and as I told you, I want to focus now on two work we did in this area, mostly in the area of federated learning. One is what's called a system that we built. It's called FLAS, which is federated learning as a service. And another one is privacy preserving federated learning as a service, which builds, of course, on the, as you can imagine, on the first work. Okay, well, brief introduction of what federated learning is. I guess most of you might be familiar with, but it's a way to train a model in a distributed way. It's different from distributed learning. In the sense that federated learning, you have the model that is bootstrapped by a centralized server. And this model is then shipped to all clients. Well, not to all clients, so a bunch of clients or subset of them. And this model is personalized on each client let's say, using all the data which is on the client itself. And after the local model reaches until each local model reaches convergence. So the data doesn't leave the user. And that's very important because there is no privacy leakage, because the data stays on the user side, the model is trained, and then all these models are sent back to the server, which aggregates them. And this process iterates over epoch. At a certain point, you reach a model which is similar, very similar or exactly the same performance as you would have in terms of accuracy, as if you were training in a centralized fashion. So federated learning, there has been a lot of work. I mean, a few companies have deployed that actually. Mostly for mobiles environment. There have been a lot of work in heterogeneous environment, and balance problem, non-ID. I mean, there are many work. I mean, there's been, let's say, a couple of years or 3 years of work, intensive work in this space. What we found that, at least from us, was missing in this landscape of federated learning is that they were all developed for single applications. So there was no way for different application or different service to build a federated learning model across different third-party applications. And so how can we do that? And then in order to enable that, what is very important in this case is that you need to be able to give permission and make sure privacy is managed properly so that data model are not leaked or shared whenever it's not whenever this is not wanted from the owners of the data and of the model. And then another thing that there was slightly less work as well across the space is that can we use a property of the network for bad data file convergence? So can we use a hierarchy? Can we do that in a peer-to-peer fashion? Can we do that without compromising the privacy and the file convergence? And can we do that in as a service model? I think that you're all familiar that the main big players have these machine learning as a service platform, wherever people that even without knowledge about machine learning or very little data science knowledge can go and use them. Can we do the same for federated learning? And our answer to this was FLAS, which we call federated learning as a service. whose main goal is actually to provide is as a service model with high-level API and SDK, so that people, people in services without much background can integrate it in their application or in their services and run it without much knowledge, and actually enable collaborative training across multiple services and application. Also, it would enable hierarchical construction in a distributed fashion, not only in typical 2 layers of federated learning where you have the central server and the clients, and there are just 2 layers. Can you do that? And that's that's what the system does. And here I'm putting some examples. For instance, you can run it typically on the left-hand side on the phones, which is what typically people have done. But you can incorporate edge nodes, with edge computing. So actually, you can also even do in peer-to-peer. There's some time work called peer-to-peer file. I'm not going to go into this now, but there is some work there. Or you can even incorporate devices in the home, for instance, the one that the telcos have, like the gateways or the home devices of that. And we had this, these 3 use cases in mind. One, okay, the typical case of a company that wants to do FL, it doesn't have the knowledge, the skill, and just wants to use an open SDK and an API and doesn't want to build anything. But the second use case is where 2 of them want to collaborate, for instance, for building a better model for a given service. Okay, give here example of Instagram and Facebook that wants to put together the user base and data without sharing any data, but building a better model. Okay, maybe these are not the companies that need that, but smaller companies may see an incentive. And third use case is where 2 companies collaborate together to solve a different problem than the original problem. For instance, rather than just recommending a song, you want to recommend a song depending if you're on a given route or not. So you need to put together models and data from different perspectives. In our system enables to do that in a fully privacy preserving and management and with the right permission management on that. You can find the details on the paper. And what we showed in this early prototype implementation is actually you have the same memory and the cost, same system cost, a regular FL, and the collaborative model building actually provides benefits with respect to it. Again, happy to talk more about that. We are now testing it in large scale and finalize the design and the evaluation, but there is some already early result about that in the paper that I'm listing here. And okay, after the optimistic view, okay, federated learning can help. Let me give you a little bit the pessimistic view again. But okay, federated learning can also lead to privacy issues. And yes, because the models and the gradients have some information about the data set. So whenever an attacker can be even honest but curious, we're not assuming a threat model where you can change the UFL process or protocol or do side channels attack, but where you can just, as an honest but curious model, listen to what's gradients or models are shared and infer information. And what's been shown is that even in the federated setting, there can be several attacks like data reconstruction attack, property inference attack, membership inference attack that can be done. Now, so how can we ensure that in federated learning, you can have a fully end-to-end privacy and avoiding such attacks in this setting? So we're intrigued by the trusted execution environments of many people today because this is becoming widespread. This is available for different platforms, both fixed and mobiles, and they actually protect the execution of instruction. And what is interesting, these are very interesting. The limitation here is that many of those, all of those actually have a very limited memory. In some cases, tens of megabytes. In some cases, can go to a few hundreds, but not much more. And as you probably are familiar with deep learning models, especially, these models don't fit within the TEs. And actually, most of the previous work in that space, what they have been doing is to use that for inference or for attestation of models, but not really to train models. Okay, how can we leverage TEs to guarantee privacy in a federated learning setting? And the answer is PPFL, which is the system that I'm presenting here. Or I'm going to give you a very quick overview now, where you basically, the only assumption is that you trust the TEs of other participants, either the server or the clients. And the threat model, again, is honest but curious, can be at the server, can be at the client, but it cannot be any side channel attack, because there have been also issues with TEs, which has been shown that by physical attacks or by side channel attack, you can get information. We don't deal with those. So the way the system works is that, first of all, you start the kickoff, the bootstrap the learning of the model with public knowledge. So this is public knowledge. There is nothing to hide. There's no interesting attacks to be performed to violate any privacy, because this is public knowledge at the server side. And especially it is important to train the first layers of the model, which are the ones that are less personalized, let's say, so the ones that are more genetic and build genetic knowledge. Now, after the model has been bootstrapped with this public knowledge, then it's sent to the client, and it can be stored and freezed, and especially the first layer are freezed and stored in the client. Now, what we do after that to fit within TE is a layer by layer training, so that these actually layers, a single layer or a bunch of layers, could fit within TE, and so you can do a training layer by layer. So you initialize the next layer after you freeze the first one, which have been trained with public knowledge within TE of the server. This is sent through a secure channel to the TE of the clients that have been selected for the federated learning process. These layers is trained until convergence using private data set of the users, and it's only trained within the TE. So this layer never leaves the TE of the clients, and it's sent back towards the same private channel back to the server, which aggregates the layer, terminates this layer, and this layer is frozen, and again is not stored outside the TE. Now, and we do that for the subsequent layer until we reach full convergence of all the remaining layer. Now, in case not all the remaining layer would fit in the TE, you can encrypt them and store them with keys which are known only to TEs, and then use later. So this is the way, actually, with this, what we show is that it is actually able to protect against typical at least known attacks in an honest but curious setting for privacy. We perform such attacks in our system. We're not able to distinguish from a random classifier. What we show also in the paper is that this machine learning model have been this way of the same utility of the models that are trained in a traditional, let's say, federated learning setting. Actually, in some cases, we even need less communication cost, because we don't need, training layer by layer actually turns out to be beneficial to the model per se as well, because of the personalization. And actually the performance cost in terms of system, it's very limited, let's say 10, 20%, depending on the metric. And what's interesting is that with this layer-wise approach, you can actually fit different sizes of TE and the heterogeneous environment, which is again an important problem in the federated learning setting. So, please check out for more details the paper that's actually going to be presented today at Mobisys, and we were so happy that we received the Best Paper Award. So I really encourage you to look at that. Code is open source, so you can go and play with it. I will be happy to talk again more about this topic. Now, let me a little bit conclude, and I hope I managed to transmit you some knowledge about these fields and what we've been doing. And the few messages that I hope I managed to convince you to do is that machine deep learning can actually be beneficial to operation, and it can improve network operation on the top of what's existing, and can make things easier and improve the quality of experience for the final end customer. It doesn't need always to be very complex system. It can be very simple, more traditional machine learning approach, but in some cases you need more complex approach, and you have to take into account many constraints when you do apply that, like the lack of ground truth, explainability, and the lack of information that sometimes you have to build with that, and it applies to different platforms. What I want to say is that despite there have been 10 years of work, this area of AI applied to work, I would say, is not really a full, complete, mature area, in a sense that we still see a gap in the latest cutting-edge deep learning solution, which are typically applied to area like audio, speech, and NLPs, and what happens in the networking area. I think we need more work to make tools customized and adapt to network engineers to the networking area. I think we also need to change a little bit the approach we have sometimes in the networking community when dealing with data set and this kind of model training, because there is a lot of synergies and important work still to be done in this area, I think. And we see more and more interaction between these two communities. I think that's very important and still needs to continue. So besides that, I also hope to show you that machine learning is not the panacea. There are some issues which can be a part of the robustness that you can deal with bringing together existing tools with AI, but there can be security and privacy issues coming from the complexity of the network and the model. The good news is that there is a solution for that, and there is work on that, and people are considering this already as an important topic. And there are still more work to be done in this area. And again, said I'm happy to talk more about those, and hope we can follow up with some potential collaboration about it. And yeah, I'm done now with my presentation, and happy to take questions and discuss.
So thank you, Diego, for this nice overview of all the activities you have in Telefonica Research. Thank you a lot. Any questions in the audience? Don't hesitate and unmute to ask your question. Well, I will start with some questions from my side then. I have some questions, in fact. So you are talking a lot about IoT and machine learning, but can you give some concrete examples about the purpose to use machine learning in IoT?
Okay, so
that you have in mind.
Yeah. So one thing that we have seen it useful even in production environment, it's whenever you have these IoT platforms, which are the ones that provides these global SIMs and provide added values to customers besides the management of the SIMs itself.
What kind of IoT platforms are you talking about?
So these are there are these platforms which provide connectivity. Basically, they are connectivity provider for IoT device. So they don't provide the IoT device; they provide a SIM. And they provide an interface and a platform where you can manage the SIMs, like enable, disable, look at consumption, activate, deactivate, this kind of platform. And there, what we have seen that was interesting is to monitor and forecast the consumption, monitor and forecast the usage, and detect anomalies. These were added values elements that were important for the customers, and that's something that's a typical way that we have seen this actually interesting even in real world production. Another one is to work in this platform which provides, again, not on the platform, but on the underlying networks, whenever you have to detect anomalies at the different layers of the chain that I showed earlier. To show anomalies in the behavior, can be anomalies because of lack of coverage, can be anomalies because there is an attack ongoing on a SIM. This is another example where this can be beneficial. Now, this is more from an operation point of view. Now, there has been quite some work in the area of privacy for machine learning devices. So whenever you want to learn something from the devices itself, using privacy-preserving ML, it's an increasing trend. Some companies have deployed, for instance, already federated learning. Google, Apple, they have that deployed, for instance, for the keyboard or for the pictures. They use that. And that's a way where, okay, this is more on phones, not necessarily on IoT devices, but you can do that on your, for instance, on your Google speaker, so they do this also on those. So that's another angle where this can be. Another way where I think there's a lot of benefits in machine learning applied to IoT is whenever it has to do with the human behavior. So of the way the humans interface with IoT. So to learn, so for instance, for audio, speech, images. So these multimodal machine learning approaches where you detect, for instance, the scene or the understanding of the people in a room or the behavior. This is a lot of cases where IoT and machine learning come together. Now, if you think even of camera as IoTs, then people counting, cars counting, plates recognition, these kind of devices are based on deep learning models in the end, because they use that. So this is another example where IoT and machine learning deep learning comes together. So depending on the context, there are many of those that have been, some of them actually been deployed in production. Some of them are more in the research side. But there is a lot there. And I think that more recently, there is a lot of this trend about privacy preserving ML, which comes even more into the IoT, because IoT is very very strictly related to human behavior and user data. So that is where I see a lot of potential benefits.
And about the platforms, do Telefonica propose an IoT platforms for its clients, either enterprises or people?
Yeah, Telefonica as one of those platforms. Yes.
It was a bit my question also. I don't know.
Yeah, Telefonica is one
do
of
not
those
have
platforms.
Telefonica in France, so I don't know what they propose.
Yeah, it's mostly for enterprise, but yes. Well, actually, Telefonica has created, but mostly for but Telefonica has a new area. It's called Telefonica Tech IoT, where actually this platform is part of, but it's an entire area which works in the IoT space.
Okay. Any questions?
Yes. I have three questions from me and Natalia.
Hello.
So, hello, Diego. I hope you're doing well. So first question, very easy. At the moment in your slide, you talk about PP fashion, and I don't know what is PP.
Privacy preserving.
Sorry?
Privacy preserving.
Ah, okay. Okay, so it was the easy question. My second question is, in another slide, you talk about orthogonal use cases, and you try to, if I understand well, apply AI on those orthogonal usages. So, for example, Google Maps and Spotify. What are you trying to do by mixing Spotify and Google Maps? It's not clear to me, because if I'm correct, Spotify is to listen music, and Google Maps is to have a map. So what do you have in mind?
So there was I was trying to give an example of a use case where two different services can build a model which is different from the one they can build by themselves for a different use case. For instance, you said correctly, Spotify provides music, so it recommends the next song to be listened, right? And Uber does, or Google Maps, okay, it does a map, so it shows you where to go. So putting together this kind of two data set, you might do a recommendation given on a route of a user. If it's going towards home, it's coming back, mixing data from the movement of people and the knowledge that they have and the songs that they recommend. So you can do a recommendation based on system. So you need extra information crossing the two. So this is an example of where basically it's a third use case where mixing together two different use base, not necessarily mixing the data, because you might don't want to share that. You can build a joint model. There are different ways to do that in a PP fashion, let's say. But the goal is to build a third use case that you would not be able to build by yourself because you don't have that service already.
Okay, so the idea is, for example, if I go to work, I want to listen metal to get energy, and if I go to Versailles, I want to listen Lully, for example.
For example, yes. And I think this is more interesting for smaller enterprise than big players, because maybe Google already has also Google Music, so you can get your own from your own data. Yeah. But for smaller enterprise, I think there is a lot of value in these use cases where you bring together technologies. Bring together different contexts and information. So that was the goal of that third party, and it's something that we have not seen in the federated learning setting. We have seen some people trying to customize for different tasks, but not bringing together this. So that was the goal of this FL as a service.
And last question, in one slide you are talking about coefficient omega for cost reduction when managing the failures. It was not really clear to me what is this omega and how did you plot those curves. Yes. So could you elaborate?
Yes, I didn't say what the omega is, so it's true.
Okay.
So that this was not mentioned. So basically, when in that specific use case, out of the tens of millions of lines of failures millions of failures that we had, most of them were very short in time, like 90% were less than 1 hour, and only 1% of them was one that was considered by operation permanent. So you can see this is a typical very, very unbalanced problem. So to deal with unbalanced problem, there have been two approaches. One is there are some pre-processing technique that try to balance the data set or inject extra data. I mean, there are different approaches. And another one, especially whenever you work with random forest or distributed strings, there are some parameters on the model that you can play with to try to balance or give more importance to the unbalanced class so that you can get more. So this omega parameter is actually a parameter that try to balance for the imbalances of the class. And what it turned out is that in the end, playing with that parameter or playing with the classification threshold was giving very similar result. And actually playing with the classification threshold, so finding the best operation point of the machine learning model, you know, in the ROC IUC curve, or in the, actually in this case, we look more at the precision recall curve. The best operation point was to play with the threshold, and changing the omega doesn't really give any benefits. And so that's the goal of the omega, try to balance for the unbalancedness of the problem. But it turned out not to be useful. We tried other things that we didn't put in the paper, like the pre-processing, but even that really didn't help. And what it turned out, instead of putting the ROC IUC, you know, the typical ROC curve or the precision recall curve, it was more useful to plot this cost curve, because that was in the end what operation we're caring about. And so we found the best operational point within that curve. The omega didn't play a role.
Okay, but how did you compute the cost saving given your x-axis? I don't remember. It was scenario 1 or scenario 2. How did you compute this?
So there are two parts of the cost. So on the one hand, there is the cost of sending a technician to fix a problem. Okay, this is a fixed cost, which depending on the distance, it's more or less. And then that's what is your cost in sending someone to fix the problem. The other cost is the revenue losses, because if the site is not fixed, the more the time it passes, the more you lose customer, the more you lose revenue, because you're not sending anyone. So depending on the ratio between the two costs, the cost saving can change, because you can wait a lot for a cell site that doesn't give you a lot of revenues, but at least when you send somebody, you are sure that the problem is a problem. But if you wait a lot for a site which is bringing a lot of value, then your cost is increasing. So the x-axis was actually this ratio. I cannot put the actual cost that we had in production for obvious reasons.
Of course, yes.
So I put this ratio, and depending on the ratio,
I guess that you had on your side some numerical values to
yes, to this two, and then I plot the ratio.
Okay.
And the baseline was to wait 24 hours. So the reference baseline is like, okay, let's wait 24 hours. After 24 hours, we say, yes, this is a problem we really need to go and fix. And the benefits are computed over that for the numerical values that we put that I cannot reveal.
Okay, thank you for the clarifications.
No worries. Thanks for the questions.
Diego, I have a continuation for the second question of Marc Olivier.
Yes.
It was about the usage of federated learning in what I think it was your second use case, learning for two different but somehow similar application services. What is this made me think about what we also call transfer learning. So for you, what is the difference between the both, and why is it better to use federated learning or better than transfer learning, or maybe it's not applicable? I don't know.
So I think you got cut at the part of the question, but
I
think your question is.
For this, so it was for the learning of two different but somehow similar application services. This made me think about transfer learning. So what is the difference?
Okay, well, the two are not incompatible. So the concept of federated learning is not necessarily the way you learn per se, but it's, it's not the way you solve the problem per se, but it's the way you build the model. So instead of training a model in a central, you get all the data, you put them on a centralized site, you train the model, and then the model is trained. You don't move the data. You move the model from the server to the clients, you customize it locally, which gets close to transfer learning, by the way, because you build the knowledge and then you personalize it. So that's transfer learning in a sense. And then you aggregate it back. And this can be for different models. It can be for audio, for video. It's mostly for deep learning, or for model where you can aggregate the gradients at least. So that's the main goal of federated learning. Transfer learning is to take a model where no matter how you train it, and you apply it quickly to a new model without bootstrapping from scratch. So the two are not incompatible. They are different. They solve two different problems. But what you do whenever you move a model from the centralized server, you bring it locally and you personalize it. That's very close to transfer learning in a sense, because you start not from scratch and you personalize it for yourself. Transfer learning, now getting back to the concept, you could do what you said doing transfer learning, like two companies, one shares a model and then move it to the other one and you do transfer learning on that. Yes, you could do that, but then you would reveal the model per se. In the approach that we have here for federated learning is that you don't share necessarily the model, you might share the gradients, or you just share the knowledge and you merge. But yes, what you want to do, what can be achieved with transfer learning, the thing there, the difference with federated learning is that you don't have to build the full model and transfer it. In every client, you learn your local model and then you aggregate it, and the global model comes at the second stage. But every node does it in its own local environment without transferring the data. That's the difference between the two. I hope I was clear, but I'm not sure.
I think so. Yeah, I don't know in details the two solutions, but I think you were quite clear. And I wanted to have your opinion about that. And, thank you.
Transfer learning actually has been shown, I didn't mention here, but it's been shown very useful very often, especially in the, it was not our paper, it was another work, always at Mobicon, where basically they were bootstrapping from one cell site to another cell site. So you learn from a set of cell sites, you transfer the knowledge to apply to another cell site. So to quickly learn about it. And that was a good case where actually that was shown to be useful. And this could be applied also to other network contexts whenever you bootstrap from one location to the other.
Yeah.
And we didn't do it in our case. We treated all the cell sites in the same way. But one way also to improve that, again, was another work, was showing to cluster, the cell site according to locations and to the characteristic of the cell sites, and then do models which are different across cell sites. Whenever a new cell site comes in, you do the transfer learning and then you train. So that's a way to quickly also bootstrap a model, which we didn't apply in our case, but it's actually been shown fairly useful, at least in the mobile environment. I'm pretty sure that in other environment you would find it useful as well.
Okay, thanks. Any other questions?
Yeah, I have a side question for Diego.
Sure.
In a field where actually transfer learning is very valuable, it's about NLP. You mentioned that some of your team is working on NLP. Can you elaborate on a few use cases that they're using? Is it mostly chatbot related stuff or?
Okay, I'm not the expert on this, but it's mostly related to speech to text work in the context of, for instance, home assistant.
Okay.
So for that, this one area. Another area, it's very useful whenever you work with books or text, and you do some analysis on that kind of work. So it's bots or home assistant, let's say. That's an area where we are very active, and the teams is working on that. And another area is handling of text and books, for which we have some use cases as well. These are the cases where that part of the team work. One place where it's very interesting NLP is to look at when you look at ticketing information. And that's a lot of NLPs because very often tickets don't have a specific format. It's handwritten by people. So doing NLP to understand what was actually a problem.
And the language is very different to what you find in books and stuff. Yeah. So.
Exactly. So that's another place where NLP could find in a very, very different environment. And those are I would say the main use cases where we worked on and that part of the teamwork.
Okay, thanks, Diego.
Diego, if I may, you've been sitting on a pile of IoT data. I was wondering, have you seen any sort of evidence of industrial IoT deployments like robots or drones or anything controlled in an industrial way? And perhaps you can comment about this.
So we have been seeing in one of the paper, we have been looking at smart meters. Which I don't know if you call that industrial or not, but that is an interesting case. There are quite some connected cars that are also of our, that we have seen in that one, ATMs, elevators. There are many of those cases. Now, industrials per se, I think it's something that is growing now, not necessarily something that we have been looking at. If you think of smart factories on this kind of thing within a factory, then we didn't really study those. This is an area which is actually quite growing, but not those ones. But the other ones, typical, ATMs, elevator cars, smart meters. Smart meter is pretty big as well. I think that in the paper of one of those, there are 3 use cases. One is connected cars, and the other one is the smart meters, which are important.
And a question about failures and the work that you presented. You were trying to basically detect and understand whether a failure should be acted upon. Anything about predicting failures or kind of estimating, let's say, where a failure is going to be happening next? Is that possible from the type of data you have access to?
So with the same data, we did 2 other use cases actually. So what are the sites which are more likely going to fail? next, which is more or less what you were predicting. So based on history, which is the site which is gonna last next, and within a given site, at which time you're gonna have a failure later. You know, which site is gonna fail next, and within a site, in how many hours the site is gonna fail. So those are all the two use cases that I didn't put in the presentation that we also handled. The answer there is that with the data we had access to, the good span for those predictions is 6 hours. When you start getting to 12 hours, it was very difficult to predict, and precision and recall were significantly dropping. Because we were only able to get, we are getting alarms plus some information about the local cell sites. To get better, we would need radio KPIs that we didn't have at that time. But I would say span of 6, max 12 hours was fair. 6 hours was good, 12 hours may. More was complex with the data we had. And yes, we could predict with the 6 to 12 hours with a good approximation, or below 6 even better, but of course then it gets less interesting.
It depends very much on local characteristics such as weather, or is it
yes.
more complex?
It's a local characteristic plus the sequence of failure that you could see happening. So if in the last 3 hours you have seen some alarms starting piling up, and then at the consequence of these alarms, then a given failure happens. So it's the combination of the two. The thing is that if the alarms were popping up in the last 6. So we collected over the past 24 hours, but the main, and it was useful to have this information at 3, 6, 12, 24 past hours. All of this was improving, but the main improvements were between 3 and 6 past hours. And after that, you could see when the next failure would happen, but not longer than that. So it was the kind of alarm that were turning on in the last hours and the cell sites characteristic, but no longer time because we couldn't get longer trends. Maybe radio API could help on that. I'm not really sure, depends on the failure, but that is the kind of elements that were providing predictions.
Okay, thank you. It was a very nice talk.
Other questions? So thank you again, Diego, for your talk.